Hello everybody, it's Mr. Arocena, and on today's video we're going to be talking about buffers. Now, what is a buffer? A buffer in chemistry, at least in acid-base chemistry, is any substance, or I guess a solution, that will prevent the pH from changing by any significant amount, at least up to a point. A buffer is created using large amounts of a weak acid and its conjugate weak base. So I guess large amounts of a weak base and its conjugate weak acid will also work. So an example of a buffer solution would look something like this. You have a large amount of weak acid here, and then you have a large amount of its weak base here. The basic idea behind the buffer is that this substance here, the weak acid will absorb the excess, any excess OH minus, and the weak base will absorb excess hydronium. And one neat thing is, as long as you're using this, the weak acid and its conjugate weak base, you get a really neat equilibrium that occurs. So from an equilibrium perspective, you can get the following K or equilibrium expression. So if you write out the equilibrium expression as we normally would, where we have products over reactants, we get the following, where the Ka is equal to the concentration of products over reactants. Now, because we have equal and large amounts, or not the large amounts doesn't matter, but because we have equal amounts of its weak acid and weak base, mathematically these two can actually cancel out in the equation, and we get the following, where the buffer solution has a Ka that's equivalent to the concentration of H3O+. And then by extension, this can calculate the pH of the buffer. This is really important because the pH of the buffer basically means that that's the pH that this type of weak acid, weak base combination will try to maintain. So if this buffer solution maintains, say, a pH of 6, then if you make the buffer solution properly and you add it to a solution, its pH will remain around 6, even if you add excess acid or excess base. Now, the preparation of a buffer, all it takes is you just have large amounts of a weak acid and its conjugate weak base. And I gotta make note of weak acid. And this is because of the equilibriums that they create. Strong acids don't make buffers because they don't create equilibriums, they just dissociate immediately. And same thing with strong bases. So a buffer has to be made of a weak acid or a weak base, and its conjugate. Okay. So let's consider why we need to use large amounts of the weak base and large amounts of its conjugate weak acid by looking at its equilibrium. So here is the equilibrium of our previous buffer solution using the acetic acid and its conjugate base. Okay. So if I were to add just the acetic acid to water, what will end up happening is that the acetic acid will dissociate into a small amount, and this is key, a small amount of its conjugate weak base and a small amount of hydronium, like really tiny, because Ka is really small, so it's going to be a very, very small amount. So if we add any excess base, so this could actually just be any excess base. Okay, it doesn't have to be the CH3COO-. What will happen here is that this base will react to the CH3COO-, or again, any base, will react with the H3O+ that's present. Now, because we have a small amount of H3O+, this will actually eventually use up, or quickly uses up the H3O+. And what will happen is if I look back at my equilibrium, if this gets used up quickly, then any excess CH3COO minus will then be forced to react with water, and it'll strip one of these from the water to create that as it tries to re-establish a new equilibrium. So you end up getting a bunch of excess OH minus, and that'll drastically alter the pH because now you have you'll suddenly gain an excess of OH minus, and that'll alter the pH quite significantly. So a buffer solution aims to prevent this shift. Okay, so you want to prevent that shift towards the reactants because, again, it uses up, any base will use up what little H3O plus is present. Okay. The extra base will remain unreacted, or it'll react with water and create OH minus. Okay. So in order to prevent the creation of the excess OH minus, we simply include large amounts of its weak base. Because then as the weak base, and of course equal amounts of its weak acid. Okay. Because if we were to look at that equilibrium again, if I have large amounts of this, creating CH3COO minus plus H3O plus, if I have a large amount of this and a large amount of this, any base I add to it, it will reduce this quantity, so the H3O plus will go down because the bases will react with the H3O plus, and then the equilibrium will shift this way. But because I have large amounts of this and large amounts of this, the concentration of this shift can go for, or the shift in equilibrium can go for quite a while until I run out of the conjugate weak acid. Okay, and the same thing can be said the other ways. If I have a base, then and it can, or if I have an acid, it can react with the water, and then this substance will shift the equilibrium back towards this way. And as long as I have large amounts of this and large amounts of this, then this equilibrium shift can handle, hopefully handle enough excess acid or base to keep this concentration from changing too much. Right. So now, does dilution have an effect on the buffer's pH? This is no, not really, because if you look back at our equilibrium expression, we get the following, where the Ka is this, but then because these are equal, they have equal moles of that, so their concentration ends up being equal. It simplifies to the following. So if you dilute a buffer, it actually doesn't diminish how well the buffer can operate. Because at the end of the day, the Ka of the buffer is just equal to the concentration of hydronium. And again, by extension, we can use this concentration to figure out the pH of that buffer solution. Okay, now what is the purpose of the buffer? The purpose of the buffer, again, as I mentioned, is to prevent the pH from changing by any great extent. The idea is that our large amount of weak acid can neutralize any base that gets added to it, and then the large amount of weak base will neutralize any acid that gets added to it. Now, of course, this is once the weak acid or weak base is used up. So once all the weak acid or base get used up, the buffer is useless. Once all the weak acid gets used, then the buffer stops working. So a buffer solution only works up until we react all of the acid and all of the base. Generally speaking, though, the buffer solution will, barring extreme circumstances, the buffer solution will do its job properly. Alright, now let's go through an example of just trying to figure out how much a weak acid or how much a buffer can actually absorb. So let's suppose we have a buffer contains 1 mole of its conjugate acid and 1 mole of its conjugate weak base. How much base can this buffer neutralize and how much acid can this buffer neutralize? Well, based on how a buffer works, the amount of base that can be neutralized depends on moles of acid. So if this is a 1-to-1 neutralization, then if 1-to-1 neutralization, and most acid-base reactions are like this, then this particular solution, since it has 1 mole of conjugate acid, then this can absorb 1 mole of base. So 1 mole of, I guess, a monoprotic base. And then similarly, how much acid can this buffer neutralize? Well, if we have 1 mole of conjugate base, then 1 mole of acid, provided the acid is monoprotic, if acid is monoprotic. If the acid was diprotic, then it could only absorb half that much. Okay. But for the most part, though, we tend to deal with monoprotic acids and bases, for the most part. Right. Now, a titration curve for buffers, you can actually see this when you discuss, since buffers are made of weak acids and weak bases, we use the titration curve for a weak acid or a weak base. And you can actually see the buffer region in the titration curve for these substances. So here is part of the titration curve. And notice here, if this is pH, the pH here is relatively constant. So we have a mostly constant pH for this region here. And eventually it'll spike quite high. So this buffering region is the amount that or basically determines how much buffering solution you have, how much of the buffer is present. The more buffer we have, the bigger this pH range, or the bigger this range, or longer this range will be. Because as we'll have to add more volume in order to cause it to spike up here. At this point, so here, the buffer is used up. Buffer is used up at that point. Okay. Now, anytime, like I mentioned here, anytime you titrate a weak acid or a weak base, you create a buffer solution. Because what we're really doing is we're adding a large amount of weak acid or weak base to something, and then it creates this buffering region. Okay. Now, weak acid buffers will create a solution that will maintain an acidic pH. So their pHs will remain below 7. Okay. Now, an easy way to create these buffers is to simply use a weak acid where the Ka is greater than this number, greater than 1.0 times 10 to the negative 7. Okay. So the Ka of a weak acid will actually determine the pH at which that acid will create a buffer solution. So if you create a buffer solution with oxalic acid and its conjugate weak base, the pH it buffers at will be equivalent to negative log of its Ka. It's really interesting. So if I look up oxalic acid, so oxalic acid has a Ka of 5.9 times 10 to the negative 2. And we calculate its pH at that Ka. We get a pH of 1.2 approximately. So this will be, if I want to create a very acidic buffer, so if I want to keep my pH at 1.2, I would choose oxalic acid as my preferred buffer solution. So it'd be oxalic acid and its weak base. And that'll create an acidic buffer. A basic buffer does the opposite. A basic buffer will try to keep the pH above 7. And much like before, we simply choose a substance where the Ka of the substance is less than 1.0 times 10 to the negative 7. So an example, what pH will a phenol buffer solution be at? So again, we can go pH is negative log of its Ka. Phenol has a Ka of 1.3 times 10 to the negative 10. So this will create a buffer solution with a pH of about 9.9. Alright, so there you go. So that's what buffers do. A buffer just maintains a pH at a specific level, and you can find out where that buffering pH will be by using this equation here. This is the pH of the buffer. Alright, so your assignment then for today will be as follows. And if you guys have any questions, you guys know how to contact me.